So last class we were dealing with domain and range, and we were talking about our different kinds of notations to be able to write your domain and range in. So today we're going to talk about restricted domain. So for a majority of functions, the domain is all real numbers. Remember, we can write that with those three little letters, X, E, R, where the E is kind of like a little C. The R's got a double line to it. So pretty much that's always going to be your domain. So if you're given a graph, it's got arrows on both ends of the graph, so your domain is all real numbers. It could be everything in existence. So let's take a look at our parent functions here. Parent functions just simply means most basic form. It's the most basic form of those kinds of functions. They refer to it as your parent function because then what happens is you take your most basic form and you move it around the graph, and then those are all the other ones. So you move it away from your parents, kind of like your children move away from their parents eventually. So that's why they call them parent functions. So our kinds of functions we have are a constant. Our function rule for a constant is simply f of x equals c. C is just a number. So c equals a number. The number changes, but c equals a number. It's represented by a horizontal line on the graph. So that's our constant graph anytime you have a horizontal line there. So your domain for your constant is just x is an element of the reals. It's every single number, as I said. Your range, however, is just y equals c. Whatever that constant value is, that is what your range is. And it's that same number for every single point on that graph. So y equals c is your range for that one. So our next one is our linear function. That's our mx plus b. Hopefully we're very familiar with our mx plus b. M represents our what? Nope. And b is your y-intercept. Slope, y-intercept. Your graph is a diagonal line. Our graph right here happens to be a positive sloping line. You can have negative sloping lines. Our domain for our linear functions, again, x is an element of the reals. X can be every single number. Your range is also going to be y is an element of the reals. Y could be every single number for your linear functions also. So next we have absolute value, which are those straight up and down bars that some people sometimes confuse as ones, but those are your absolute value bars. Do you guys remember what it means, what you do with absolute value? Michael? Perfect. It's how far it is from 0. So it just turns whatever number you have into the positive version because you're just looking purely how far from 0 am I, not direction. Positive, negative tells you direction. So again, domain, x is an element of the reals. Could be everything. Now for this graph that I have here, for my range, my lowest value is right here at 0. And then it goes up. So y is greater than or equal to 0. Now your range would change if I moved my graph down. It would just be greater than whatever that number is when I moved it. Or if I moved it up, same thing. So your range value can change for that one depending on where your graph is. Next one is our quadratic. So f of x equals x squared is our most basic form there. Again, domain, x is an element of the reals. You can use every single x number in existence. Will we ever have a negative on this graph for our quadratics? In our range anyways? No. So y is greater than or equal to 0 for this one. Again, as I move it, my range will change, but for my parent function, it's y is greater than or equal to 0. And then our last graph here, this is our cubic. So f of x equals x cubed. So x is an element of the reals. That's our domain. Our range for this one is also going to be element of the reals. It could be every single y value for this one. So you should be familiar with this chart. I'm not saying you have to memorize domain and range, but you should be able to figure out what they are by at least looking at their graphs. And if you always have an equation, you can always use that calculator of yours to help you figure out what the graphs look like so that you can figure out your domain. So now we have three special cases when your domain is not an element of the reals. It's always an element of the reals except for these special cases here. So it would be these three graphs that we have right here. Kind of funky looking graphs here. So this graph is the equation f of x equals 1 over x. This graph is f of x equals the square root of x. And this third one is f of x equals 1 over the square root of x. These are the three instances, again, where our domain is not simply an element of the reals. It's not all real numbers. So let's look at case number 1. The issue with case number 1 is the fact that it's a fraction. 1 over x. X is in your denominator. So the restriction for this is your denominator cannot equal 0. Because remember, you can't have a 0 in the bottom. If we had a 0 in the bottom, it would be undefined. 0 in denom is undefined. So let's see here. An example. Let's say I had the denominator, or the fraction 1 over x minus 3. So I have x minus 3 as my denominator. In this instance, x cannot equal a 3. If it did equal a 3, in my denominator I would end up having 3 minus 3, which would give me a 0 down there. We can't have that. That's never okay in our fractions. So whenever we have this situation and we're trying to figure out our denominator, our domain, what we do is we set the denominator equal to 0 and solve. So what that does is that gives us the value that we cannot have in our denominator. We set it equal to 0 and solve. So looking at our second case, our radical there. The problem with this one is the fact that it's a radical. So the problem with our radicals is you can't have negatives, no negatives, under the radical. Remember, what happens if we have a negative under the radical sign? What does it turn into? Imaginary. If we have a negative under our radical sign, we have an imaginary number. We can't have that. We can only graph real numbers. So, no negatives under the radical. So let's see, here was my example. So the square root of negative 25 would be plus or minus 5i. I can't graph that because I'm not graphing on an imaginary plane. So what we do is we set the radicand, which is the stuff under the radical. We'll put that in there, under radical. Greater than or equal to 0, solve for x. So if it's greater than or equal to 0, that means it's going to be either 0 or a positive integer, which is what we want, and we can have under our radical signs. So that would help us find our domain. So then our last one is a radical, and it's in the denominator of a fraction. So a radical in denominator of fraction. So really, it's kind of putting those first two cases together. It's taking the fraction, it's taking the radical, putting them together. You have a radical in the denominator of your fraction. So the two restrictions we have is the fact that the denominator cannot equal 0. The radicand has to be greater than or equal to 0, because remember, it can't be negative. So it could be 0, or it could be positive, can't be negative. So for that example, you would see 1 and 2. Combine those two together. Why we can't have a 0 in a fraction. Why our radicand has to be positive or 0. So for this one, you're going to set the radicand just simply greater than 0 this time. We don't want the or equal to, because it can't be equal to 0 in a denominator. So it's just greater than 0. And then solve for x. Okay. What's up? All right, let's take a look at the next page. Asymptote. You guys remember hearing that word asymptote? I always remember whenever I say this word to my freshmen, they always just start giggling. So an asymptote is a line that a curve approaches but never reaches. So it gets closer and closer and closer and closer to a line, but it never actually reaches it. So if we look at my graph over here for a second, this is my graph. F of x equals 1 over x minus 2. I know it's equation because I typed it in the calculator to get the picture. So our restriction is what value would make my denominator here a 0? What could I put in for x that would make it a 0 there? 2, yeah. So x cannot equal 2. So if you look at your graph here, there's kind of this imaginary line where x is 2 that the graph is approaching. It's getting close to it, but it's never actually going to reach 2. So your asymptote, used to represent the undefined values, of a function. So like, for example, our undefined value there of x equals 2, it can't be 2, because then it would make a 0 in our denominator. So it's represented by a dotted line. Always your asymptotes are dotted lines at the undefined values. Now, because this one did have a vertical asymptote, it's got that 2 it can't equal. It does also have a horizontal one. If you look at it, these graphs are approaching your x-axis, which is y equals 0. But they're not going to actually touch or cross that line. So this one actually has both a vertical and a horizontal asymptote. So if you look in your calculator, wherever there is an asymptote, it tells you error. So let's see here. I'll type in my equation over there. So I got 1 over x minus 2. So there's my graph. We look at our table. I'm going to go to where x is 2. There it is. Graph tells me it's got an error. Calculator tells me it's got an error because that's your undefined value. That's what it can't equal. So the calculator can kind of help you figure those ones out too a little bit. And so where the asymptote is located, indicating the values in which the function is undefined. So that error in the calculator helps you out with finding your undefined values. So let's actually go ahead now and practice finding our domains with our restrictions. So the first one is a fraction. Our fraction, what we said to do was take the denominator, set it equal to 0. So x plus 7, I'm going to set it equal to 0. And now we're going to solve for x. So I subtract x. And I am getting x equals negative 7. So that means that is the value x cannot be. So when I write my domain, I'm going to use my set builder. We start off by saying that x is an element of the real, so x is everything. And then we put comma, x cannot equal negative 7. So that tells us it's everything except that one value of negative 7. All right, let's try the next one. So again, another fraction. So I'm going to set my denominator equal to 0. When it comes to finding the domain, doesn't matter what that numerator is. It's all about the denominator. So let's see, I subtract my 6. Divide by 2. And so we get negative 3. Negative 3 is our one value it can't be. So our domain, x is an element of the reals, except x cannot equal negative 3. So let's try our third one. Again, still fraction. So I'm going to set my denominator equal to a 0. Only difference this time is my denominator is quadratic, so I'm going to have to factor. So x and x gives me x squared. What multiplies to 6, but will give us a 1 in the middle. 3 and 2, so negative 3, positive 2. That's how I'm going to get my negative 1 in the middle, negative 3 plus 2. So then I set them both equal to 0. So I get 3, and I get negative 2. So we got two values that it can't equal this time. So I'm going to start with my x such that x is an element of the reals, comma, x cannot equal negative 2 or 3. Questions on those fractions ones? Okay. So let's practice some radicals. So with the radicals, the whole thing about it is it has to be 0 or it has to be positive. So all you have to do is take the stuff that's under the radical. So in this case, the only thing under the radical is x. And you're going to set it greater than or equal to 0. And then you're supposed to solve, but there's nothing to solve because x is already on its own. So that is our domain. X is greater than or equal to 0. You don't have to write XER this time because the inequality tells you all the various values that it could be. Whereas before, when it was just that it can't be -3, you have to say it's everything else. So you got to have that XER there. All right, 5. So again, I'm taking the stuff under the radical. That's known as your radicand. I set it greater than or equal to 0. This time we do have to solve for x. We just have to add 1 over. So we get x is greater than or equal to 1. And then again, there's our domain. X such that x is greater than or equal to 1. Again, the stuff under the radical sign, greater than or equal to 0. And then we go ahead and we solve for x. So I'm going to add my 15 first. I get 5x is greater than or equal to 15. Divide by 5. And I get greater than or equal to 3. X such that x is greater than or equal to 3. Now that sign will flip. Remember, if you divide by a negative, it would flip and become a less than. These examples didn't have that, but that is possible. It's not always greater than. So then our last two examples here, these are the combos. It's a fraction and it's a radical in that bottom part of the fraction. So we still take the stuff under the radical, but this time it's simply greater than 0 because it's in the denominator. It can't also be equal to. So this is our case where it's just simply greater than 0. And then we solve for x. So I'm going to subtract my 4. So x is greater than -4. There's our domain. I forgot to take off the squared in that last one, guys. That should just be x minus 9. So x minus 9 greater than 0 because it's in the denominator of a fraction. Add 9. And x is just greater than 9. That's our domain.